Alright, for the Unit 4 performance task, we have 3 options as usual. The first option is to create your own vertical motion problem. So this might sound very similar to some other options that you had in the last 2 performance task units. And it is. However, this one specifically needs to be like a vertical motion problem like we did in class where well, I'll just read the rest of this first. So use research to make your problem as realistic as possible. Write a word problem explaining the vertical motion scenario and identify the starting height, maximum height, and landing point. Remember that vertical motion problems have time on the x-axis and height on the y-axis. So that's important. A lot of the real-world examples of quadratics don't have that. They have position on the x-axis and height on the y-axis. So this time just make sure that it's time. You're measuring how high something is after how long. And they also need to have consistent measurements. So if one of your measurements is in feet, like your height is in feet, your speed or your velocity, I should say, should not be in like meters per second, right? Because that won't make a consistent graph. Like the measurements need to be consistent. So all time is in seconds and all height is in feet, or whichever you pick. So I have a couple examples of that one. We have a bottle rocket question, and I am emphasizing to do some research and make sure that your initial velocities and is reasonable, because that makes it much more interesting, and also you will learn stuff along the way, which is cool. So we have a bottle rocket example and also a jumping example. So, for example, on this one you might have to do some research about how what initial velocity makes sense for a human's jump. Like, what is the average jump velocity of a human? I'm not sure. But anyway, so just do some research. It makes it more interesting and more accurate. The second option that we have is to research a 3-dimensional optimization problem. I don't have any examples of this one. I'm not sure why. I think that, I mean, I had some people do it last year, but emphasis on the word research. Optimization problems, especially when it's like volume or surface area, 3-dimensional, are tricky to solve, and we didn't have any examples of that. Besides the honors kids, we did a little bit of that, but so emphasis on the word research. I don't need you to solve a 3-dimensional optimization problem, you just need to research one. So for example, like the one in our book that for most of us we didn't solve was about the size of soda cans. And so we don't really realize this, but the size of soda cans is the result of an optimization problem, because companies want to give you 12 ounces of soda, but they also want to use the least amount of aluminum to make the cans possible. And that's an optimization problem, one where the minimum is the optimal situation. So, so when you solve that, you get the diameter of, or the radius of an actual soda can, because that is the best size. So think of how many things are created because of the exact size of soda cans. Like all of that came from solving an optimization problem and implementing it, right? Anyhow, so there are a lot of like business applications for optimization problems. So your job is just to research something that was optimized. And the other option too, you don't have to do a 3-dimensional. You can also do like the area of a shape other than a rectangle. So like a circle or a triangle. There was one homework problem about a triangle. Anyway, something that was a little bit other than what we did in class. Do research to decide what question gave rise to this optimization problem. So using our soda can problem or example, it's like, okay, what should the dimensions of this cylinder soda can be so that we use the least amount of aluminum and still give this amount of volume, right? And how it was solved. You don't have to understand the math, you just have to sort of give me a rundown of like the result, right? Option C is to choose an area optimization problem that we solved as a class. So something from the notes or on the homework. Creatively demonstrate how the area changes as one side length changes within the restriction. State the problem you're using and show why the optimal side length results in the biggest area. Go beyond rectangles to show this should be visual, not algebraic. What might happen to the area if you were allowed to use the restricted perimeter to create different shapes? Perhaps a heart shape could give you a better area, or a triangle, or a trapezoid. So this is just like a fun way to go into more of that area optimization stuff. So like, what if you were given a certain perimeter, and I had some people in class when we talked about like the optimal rectangle. They're like, okay, but what if it's not a rectangle, right? So sort of have that little thought in the back of your head as you do these problems, like perhaps a different shape would create the biggest area instead of a rectangle. But I'm going to show you an example of this one. So the main part of this is to show creatively how the area changes depending on what side lengths you use. So this was a 40 feet of fencing problem, and she showed several different possible areas. And that the one with the biggest would be this square with 10 by 10. So your choice is to choose which problem you're using, and also whether or not to include like different shapes and other sorts of options with the given perimeter. So those are your options for this time. Let me know if you have any questions.